All right, for the last lesson in this unit, we're going to use our similar triangles that we discovered, and in the last lesson, we'll use these similar triangles to solve application problems. Now, we can use similar triangles to measure the heights of objects that are difficult to get to. Trees, tall buildings, and cliffs. Sometimes they're objects that would just be very challenging to measure in the first place, whether or not it's because they're challenging to get to. Maybe they're not, they don't have a particularly flat side or something like a tree. It's tough to measure the height of a tree without using our similar triangles. They're also used by professionals to measure distances across rivers. They're also used in astronomy to determine the distance of galaxies, the distance of different stars. Now, we're not going to use them exactly for that in this lesson, but we are going to use them to determine the height of, say, a building. So in this first application, a person is 195 centimeters tall. Okay, and they see the reflection of the top of a building in a puddle 7 meters away. And it's a physics concept that the angle they're looking at this puddle will be the same angle that the building is on the other side of that puddle. But either way, the diagram's given to us, so we don't necessarily need to be aware of that concept. Now, how high is the building to the nearest meter if it's located 40 meters away from the puddle? Okay, so we know the distance away of the person to the puddle and the building to the puddle. We also know that these angles are the same here and here, and since we're measuring these heights right from the ground, then we have the right angles here and here. Since we have all of those angles, we have angle-angle similarity. And we can use this angle-angle similarity to come up with a scale ratio, and we can use, or a scale factor. We can use this scale factor to determine the height, the unknown height of the building. So we'll jump in right here, and we'll evaluate our scale factor. Scale factor equals we'll go the big triangle over the small triangle again, so that's 40 meters divided by 7 meters. And that's going to be the scale factor that we use. So if this is our scale factor, then 40 over 7 over 7 will equal the big height of the building. So that would be our similar side to the height of the person, right? So we'll call, we'll let, I guess we need a bit of a let statement in here, don't we? Let H represent the height of the building. So we have H divided by 195. And then we can isolate for this H by multiplying both sides by 195. Leaving us with an H on the right-hand side, and the left-hand side, we can plug that into our calculator if we would like. So that's 195 times 40 divided by 7. We're working with 1,114 meters. And that's approximate, so we'll put a dot above our equal sign here. Therefore, the building is 1,114 meters high. Oh, sorry, this should be centimeters that we're working in here. 1,114 centimeters high. And this, if we convert this to meters, because we're trying to find it to the nearest meter, that is 11 meters high. If we round to the nearest meter, there we are. Now we can jump forward and we can take a look at another application here. So we have a 5-meter ladder resting against a vertical wall. So let's give ourselves a wall here and a ladder, something like this. Okay, so it's 5 meters in length. There we are. With its base 3 meters from the wall. So here I have 3 meters along the bottom, if you will. Its base is 3 meters from the wall, 3 meters. Its hypotenuse, that's the length of the ladder, is 5 meters. Another ladder, 12 meters long, is resting against the wall parallel to the first ladder, okay, well, we need a bit more space here now, don't we? So if it's parallel to the first ladder, then it's going to be something like this. They'll both have a right angle inside, and let's actually change up our color here. Might be a little bit easier to see what's going on. Good stuff. So I have similar sides along the bottom, similar sides along the left-hand side, both with the same angles involved here, because this side is running parallel to our smaller ladder, right? It's running parallel in there. So our angles, we can see our similar angles inside, and we can use angle similarity. They also would have similar angles down here, again, through our F pattern, through our similar triangles. So we have here, it says, let's label in green, right along the bottom here, we have a 12, the ladder itself is 12 meters long. Geez, sorry folks, I'm struggling here. The ladder itself is 12 meters long. And we need to find how far up the wall this second ladder reaches to 1 decimal place. I assume we're working in meters here. So we'll call this H. And that's what we need to find. Well, since they're similar, we can find our scale factor equals, and we'll go with, again, the big triangle's side that is 12, right? We see our similar sides as the hypotenuses here. Scale factor is 12 divided by 5. Fantastic. Now, if that's our scale factor, we can use this. 12 divided by 5 will equal our height of the big ladder divided by the height of the small ladder. We'll call this maybe H2 for the big height and H1 for the small height. Well, we don't know this small height, so we need to find I know I'm jumping all over the place. So I know that 12 divided by 5 equals H2 divided by H1. Okay, well that's great, but I don't know this how high my small ladder is reaching against the wall. So I need to find this, find H1. In order to find that, I do have a set of skills available. That's my Pythagorean theorem, right? I know 2 of these sides. I'm working with a right triangle, and I don't know my third side. So I can start labeling in here. Opposite the right angle, that's my side C, so that's 5 meters. And I can call the other sides what I would like. We'll call them A and H1 as B. Fantastic. So I'll use my Pythagorean theorem over here. Pythagorean theorem tells us that we're working with here a squared plus b squared equals c squared. Now the unknown that I'll be looking for, it's b. And that's not isolated yet. So I'm going to isolate that in here by subtracting a from each side. If I subtract a from each side, I'm left with b squared on the left, c squared minus a squared on the right. Now I can substitute in values that I already know. That is c equals 5 and a equals 3. So I'm working here my Pythagorean theorem. B squared, that's still my unknown, equals 5 squared minus 3 squared. Okay, 5 squared, that's 25, minus 3 squared, that's 9. That is b squared equals 16. That's great. Okay, so my third side length equals 16. No, that's not true, because my highest side length needs to be 5 meters. So I can't use 16 right here. I've forgotten. We need to make sure we square root both sides. So we'll square root both sides here, leaving us with b equals 4. Okay, square root of 16, that's 4. Fantastic. That makes more sense. So this h1, remember, b was my h1. So I can put that in here. I can sub h1 equals 4 into this equation up here. So I'm working with 12 divided by 5 equals h2 divided by 4, and then I can isolate here for my h2. I can do that. Let's choose a better color up here. By multiplying both sides by 4, right? So I'm performing the inverse operation of the divided by 4 I see over here. They cancel out on the right-hand side, leaving me with h2 equals 4 times 12. That's 48 divided by 5. I can throw that into my calculator right here. 48 divided by 5. I'm working with 9.6. h2 equals 9.6. That's what we need. So therefore, the long ladder reaches 9.6 meters up the wall. And there you go. That's how we can use. Sometimes it's not so straightforward, right? We might set it up in a way that that looks really easy. Then we realize, hey, we don't have all the information. Sometimes when that happens, we can use what we do know to find the information that we need. So as long as we're setting it up this way, we can easily see which information it is we're lacking that can get us there to the answer. Hopefully you can use some of these skills you learned to handle some of the application problems in the homework.